Previously we talked about basic hill slope geomorphology, slope area relationships, and concave slopes being potentially eroding less than linear slopes. So now we're going to talk about erosion models, because we showed the results of an erosion model, which is Siberia, but we're going to talk briefly now about erosion model types. And essentially they come in three types, right? I haven't got the third type here. So there's the computer models are either empirically based or physically based. So an empirical based model is essentially you do a bunch of experiments, you establish some relationships between some parameters that are important to you, like maybe rainfall intensity and slope length and how much erosion happens, and then you use that as a guide to do your design. The other type of computer-based model is a physically based model. So this is where you incorporate the laws of conservation of mass and energy, model the physics of the process, and make predictions about what's going on, including whatever relevant processes you're interested in. And there's a whole bunch of models that exist that you can just pull off the shelf, but you have to be aware of what's going on. And the third type, which I haven't really included, but is really interesting, and it's what used to be done a lot in the 50s and is starting to be done more and more now, again, are physical models. Now that's different from a physically based model. A physical model is you actually use a real soil of some type, and you actually simulate whatever, you apply water to that soil in a laboratory situation under controlled experimental conditions, and you look at how that's evolving over time. And you can learn bits and pieces about processes. You can do design using these physical models, and the Dutch were world famous for doing this in their hydraulic models when they were reclaiming land from the sea. Designing their dikes and designing their bridges and dams, they had large-scale hydraulic laboratories that eroded soil and sediment and tried to do scaling up to better understand large-scale hydrological processes. So today we're just going to focus on the first two that I talked about, empirical and physically based models. So here's an empirical model. It's just an experiment where they've compared the erosion rates in tons per hectare per experiment to the gradient of the experimental plot, right? So slopes range from 10% right up to nearly 40%. And they come with a relationship that was almost linear, right? So this empirical relationship then could possibly be used for some sort of design. The question is, can you use that empirical relationship at a different site, on a different soil, under different conditions, under different rainfall conditions and so on? And usually the answer to that question is no. Physically based models, on the other hand, incorporate the laws of conservation of mass and energy, laws of momentum, and force balances, and they basically use the continuity equation as a statement of conservation of mass of soil, for example, through space and time. So essentially the continuity equation is what goes in minus what goes out equals the loss of matter from the system. So the input could be, for example, soil production from bedrock. The outputs could be erosion, and the difference between the two is the net loss or gain in sediment at that point. Okay, so you've got to be skeptical about models, and I'm a modeler and I'm skeptical about my own models. So that's a healthy skepticism that you should all appreciate. So if you're going to apply a model to a problem, you need to understand some of the assumptions behind that model. All models have assumptions. All models are simplifications of reality. And so you should be aware of that when you start applying the models. And sometimes not all the assumptions are made explicit. You have to look at how the models actually run to interpret what some of the implicit assumptions, what some of the unstated assumptions are in the model. So you have to look at whether the model formulation is correct and whether it actually represents the physical processes that are of interest to you. You also have to look at the calibration of the model. For example, some physical models might use parameters that represent the erodibility of soil, and you've got to look at whether that erodibility is suitable for your soil. You may have to change the parameters to be more representative of what's going on in the system that you want to make predictions in. So how reliable are the model results? Well, there are many different types of models, and one of the most common empirical ones is USEL and its various forms, subforms. There's USEL, there's RUSEL, there's MUSEL, and there's various other forms of the universal soil loss equation. RUSEL is the revised soil loss equation, and MUSEL, I can't even remember. But essentially they're empirical equations. So they, we'll come to them in a sec, but USEL and RUSEL, what they do is they look at things like the erosivity of rainfall, and they have a parameter for that. And then you multiply that parameter by another parameter which represents the soil type or soil texture. Then you multiply that parameter by another parameter, and that might represent the slope. And so multiplying all these empirical numbers together, you end up with an index for how erodible your soil is. And you can see there's going to be problems in there if those equations in USEL and RUSEL have been developed in other soils. And at the West Australian Soil Science Conference this year, and not surprising to me, but maybe to the guy who presented, he showed results where he used USEL empirical parameters to predict erosion at a mine site, and they didn't work. Didn't even come close to working at predicting the erodibility of materials. So USEL, I think, is useless, even though it seems to be a bit of an industry standard. That said, there are problems with physically based models as well, and we're going to talk about some of them. But there are, from an academic perspective, you can learn about processes using models, but you can also use them in an interesting way to make predictions and do design with, and people are doing that in Western Australia. So they're using models like WEP, Kinross and Lysum, as well as some others, to make predictions about erosion. So some of those models are just hill slope models, and then others are landscape evolution models. And landscape evolution models actually model the whole landscape. They model how a system comes about, and so how you get hills and channels and gullies and hill slopes and the whole thing combined. Some of them even include things like vegetation, like ESS, a model that I'm working on with Kyungrok Pak from Korea University. Whereas others like Siberia and Caesar and Cascade are purely physical models that move sediments around but don't necessarily consider the vegetation. And Child is another one which actually incorporates vegetation and subsurface water flow and really quite complex processes. Right, so these models have the ability to predict both short and long-term landscape development. And here's an example of the universal soil loss equation, USEL. They have an estimate for the average annual soil loss in tonnes per hectare per year. And again, all it is just a bunch of numbers multiplied together. You've got an erosivity number, an erodibility factor, a slope length factor, a steepness factor, a cover management factor, and a supporting practice factor. And this has no physical basis. There's no reason why you would necessarily multiply a bunch of numbers together like this to get an average soil loss. So you could develop your own multivariate type relationship to predict annual soil loss using all these factors based on a bunch of experiments you've conducted for your particular site. And some mine sites actually do this. They actually go through and systematically measure the interrelationships between each of these parameters in a series of experiments to come up with design. But you can imagine if you've got 1, 2, 3, 4, 5, 6, 7, 8 parameters plus a few different soil types, adding a few more, you've got a very complex experiment that you need to manage to be able to make decent predictions about what's going on. Okay, so USEL, just some of the assumptions, models inter-rill and rill erosion, right? And it should not be used to estimate sediment yield from catchments or gullies. The equation only models mean annual soil loss, and you can't use it for predicting soil loss within or from a particular storm event. So if you're collecting data from individual storms, you can't necessarily go back and pre-calibrate USOIL based on a few storms. You'd need to measure in the long term to get those erodibility factors and so on. And the model should not be applied to conditions for which the factors have not been determined, right? So a lot of the factors that were determined were based on experiments done in Purdue from the Midwest United States using their soils. And our soils may be very different. Our rock contents may be different and so on. Our rainfall, the way the rainfall falls could be very different. And so all the parameters that were developed by Purdue to those particular soils, you should treat with a great degree of skepticism when it comes to making predictions about erosion in West Australian soils. The advantages of USOIL, if there are any, I'm very skeptical about that. You can derive input parameters without field measurement. Well, that's a load of bull, if you ask me. And it works under most conditions if used within its limitations. Well, yes, it works if you've done all the experimental work at your site. So there's no getting around USOIL unless you've done your own measurements. Okay, you can't apply USOIL if you haven't done your own field calibrations, right? And you should treat it with extreme caution, extending it beyond where your experimental data was derived from. You should treat with extreme caution. So there's other types of models out there. There's the Water Erosion Prediction Project. It's a physically based model. It was set to be the next generation from USOIL. It's got a Windows interface. It's a well accepted model, widely tested, but it's not what is widely tested or is used as USOIL. Okay. And it uses a continuity equation to describe sediment movement into a rill. And I won't go into all the detail. You can look up WEP if you're interested. There's other models like Kinross, which is a physically based hydrology model. It simulates hill slopes as these little planes like this with a constant slope. Rainfall falls on there, it has soil properties which define that hill slope, and then it works out how much runoff is eroding, and then the sediment transport potential. You can define characteristics of your channels and your channel network, and then it uses the kinematic wave equation, which is down here in the bottom right hand corner, to describe the overland flow. And for example, Kinross does an okay job at simulating some runoff from a bunch of different hills and different rainfall amounts. Again, this is a runoff from a hill as a function of time. So it does okay compared to some experimental data. And it also can make predictions about the sediment discharge. And again, you should use some calibration, actual measurements of the hydrology and the sediment yield from some sites to calibrate the parameters for this model. So Kinross, for example, discretizes your catchment, or you have to do this anyway. You have to discretize your catchment into a whole bunch of sub-catchments that are hill slopes, in this case, and channelized hill slopes, JI, and then you set up your river network and then you route your flows. So your catchment might physically look like this, down the bottom right hand corner, but in the model you would discretize it as something like this, as catchment B, which is connected to this channel, and catchment A, B and C are all connected to that channel, right? And you end up with flows being routed through. So it's a semi-lumped, semi-distributed hydrological erosion model. Okay, so things to consider about Kinross, right? The hill slopes don't change as a result of erosion. So you can't do long-term landscape evolution, right? The hill slopes always have the same slope, they always have the same soil properties, they're one-dimensional hill slopes, you can't get flow conversions and so on. So Kinross's suitability for long-term prediction is doubtful. LISM is a European model, I think developed out of Spain and the Netherlands, and it's being used to make predictions about where gully erosion might happen. And so you can see a simulation here is a digital elevation model, and this is the results from LISM, where it is making predictions about where gully erosion is going to happen. There's a whole bunch of different predictions, and the black lines here are the observations of where some gullies actually did form on that hill. Okay. And so it's in terms of a risk approach, you're able to make predictions about possibly where erosion is going to be most likely to occur, and you can apply some remediation strategies in those areas to target areas that are most susceptible, for example. And that's how you could use this model to make predictions. So other things you consider about erosion, hydrology and landscape evolution models is actually how is the hydrology handled? Is it just one lumped parameter for the entire catchment, or is it like a bucket describing an entire catchment, a 0D model? Is it 1D like in Kinross, where you route the water flow through a series of separated flow networks? Is it 2D? Do you have two-dimensional water flow in the landscape? Quasi 2D or 2D, or can it actually handle three-dimensional water flow with the full hydrodynamics? Can it handle changes to soil properties and erodibility of materials? For example, can it handle armoring? And can it handle particle size of your soil materials? Does it include dynamic aspects of vegetation? Right? Do you need to consider soil production? What sort of timescales are you doing this modelling over? And very few of these models actually handle wind. So is wind an important process that you need to think about? So let me give you an example of what I mean by some of these things you think about. Here's some examples of the hydrology model. So in Kyonokamai's model, we had a simple quasi 2D model where actually we have water flowing through a network on the hill slope, but water only flows in one of 8 possible directions from one point to another. So that's why it's quasi 2D, right? Water doesn't flow in multiple directions at once. So you can have a two-dimensional model where instead of water only flowing in one of the 8 principal directions, and diagonally as well, you can actually partition the water from one cell or one part of your model into 2 compartments or more, right? And that's a two-dimensional model. And then you can have fully 3-dimensionals, which is even more complicated. So how's these guys investigated the impact of this assumption, this quasi 2D assumption, versus a fully distributed 2-dimensional model on the water flow in a catchment in, I think, Walnut Gulch in Arizona. So when they applied a rainfall to the system and then routed the flows through the landscape, this is where the dark lines here are where the highest flows were. Okay, and you can see the highest flows are really concentrated around the stream network. It's given by the topography. And the problem with that is that the flows can actually be larger than is the capacity of that local channel. So in reality, the water flow should be spilling out sideways. And a two-dimensional model can sort of handle that a little bit better. Not necessarily always, but sometimes. In this case, when they applied the same amount of rainfall to this system, the flows through the landscape were a little bit more spread out, and you had obviously more potential for erosion to occur on the sides here, and that would lead to a different geomorphology in the long term, potentially. Right. So if that's important to you, then you may need to consider a 2D model as opposed to a quasi 2D model. Right. So in conclusions, there's a whole bunch of different types of models. There's empirical models, physically based models, and physical models. You need to think about the type of model you need to apply that to your problem. Always be skeptical about the model and the claims that are made about how good the model are.